Then, perfect. So our next speaker, we're happy to have Huanchen Bao from the National University of Singapore, who will talk to us, who will give the first talk of flag manifolds over semifields. Thank you very much.
Okay, thank you. Thanks for the introduction. Yeah, it's a pleasure to give a talk here. And basically, there will be two talks on related topics, and they are actually fairly independent. It's based on joint work with Xihua. And so basically, the ultimate goal of today's talk, I want to give you a definition. So the point is to justify the definition is correct and to let you know what's the expected properties. So basically, the main part of this talk, actually, I'm going to basically survey some results about total positivity. And then at the end, I will give a definition, some generalization to semifield. And you can compare the definition that you can compare the expected properties with the setting of total positivity, that the justification, the definition is correct. Okay, I will write on the pad at the first part, and basically there are some repetition later, so I will sort of go through the slides for later part. All right, yeah, so let's get started. So the first part, as I mentioned, recall some known results. So totally positive matrices. This is basically linear algebra. So we call a matrix, I'm only consider interest in R, to be totally positive. I call this TP, and I'm pretty much just gonna call this positive if all the minors of A are positive. And I'm calling this totally non-negative and T and N. Well, very often I'm going to call this non-negative, but actually I'm often going to abuse the notion called this positive. It's by mistake, but usually it's understandable. If you see what I mean actually here. If all the minors of A are greater than or equal to 0. Okay, we have to underline. So the notion actually dates back like 100 years ago. I think at the beginning, this is by Schulenberg. It's in 1930. And I think basically around the same time. And Gantmacher and Crane. And 1935. I think that's the first study of this. And example, very easy. Of totally positive matrices. And basically for 2 by 2, it's fairly easy. We have all the entries to be positive. That's the 1 by 1 minor. And the determinant, that's basically 2 by 2 minor. We know this is 2, this is positive. So this is totally positive. Okay. And yeah, you can easily adjust notation. Adjust the matrix. Maybe, for example, making this to be 0, you get a totally non-negative matrix. And if you go into 3 by 3, this is already non-trivial. And the typical example is a Van der Waals matrix. 1, 1, 1, 2, and 2 square, 4, 8, 3, 9, 27. And this is totally positive. Okay, and yeah, this is a typical example. Van der Waals matrix. All right, and the set of totally non-negative or totally positive matrices form a monoid. Just as briefly recall, what I mean here is you can do multiplication, but there's no inverse. Okay, just briefly recall. That's the thing what we think here. Okay, and yeah, I think the linear algebra is the Cauchy-Binet theorem. If you do multiplication, the minors are still going to be positive. But yeah, you can also check this. And let me have a notation to set up. Okay, I'm going to denote the monoid or of this as totally positive matrices. I'm going to denote this to be greater than or equal to 0 as totally non-negative matrices. They are monoids. But I'm going to change the second one to another notation, which may suggest what I'm going to do later. I want to think of this as the R+ point of general linear group. And later, I'm going to replace this for any semifield. Okay, I will give you the definition semifield later, but basically it's something like this, but I somehow want to remove certain inverse. And remarks, just a little bit historical. Okay, and basically the minor definition I give here only works for general linear group, basically in type A setting, and let's take generalize this for other groups as well. Define totally positive and totally non-negative. Again, I want to think of this as R+ point. For any split group over R. And thus he actually also defined this for minimal category group. I will recall more definition later, but now I just want to you see how this how this related with this definition in the linear algebra. Okay. And his work really based on the canonical basis. But I want to emphasize one of the crucial property he used is the positivity of the canonical basis. I will actually mention more later in the talk. Just briefly demonstrating how this is connected with the linear algebra setting. Let me just sort of explaining how sort of you can do this using canonical basis in the general linear group setting, just very briefly here. So basically a matrix in this new setting, I want to think of this to be totally positive if all entries of A acting on L lambda is the highest weight module with the highest weight with highest weight lambda. I want this entries respect to the canonical basis. Is positive. Okay, and so for example, we can consider the action just on the n-dimensional space, entries to be positive. This implies well, entries to be positive. And you can also consider this action on the exterior power. And here entries to be positive implies 2 by 2 minors to be positive, and etc. And you can see here I'm not really choosing this to be regular. So you can imagine if I'm choosing my lambda to be regular, I actually, well, here it's actually I'm having a non-negative one. So if I'm choosing this lambda to be regular, we can actually see how this is going to lead all the minor to be positive. Okay, yeah, I think you can imagine how this is going to go. I will give you another way of defining this in a minute. And another remark I want to make is basically sort of let you know this theory of total positivity has connection with many things. The theory, that's right, the theory of total positivity has connections with, well, the first one, cross algebra. And this is also connected with higher Takemura theory. This is by the work of Fock-Goncharov. And recently, there is also a very popular thing called amplitude that's from the physics side. Physics. Okay, I'm not going to expand too much on this because I think any of those three, well, there are many other connection, and just say etc. I'm not going to expand too much on any of the connection. That's going to be too far. But basically, I want to share just briefly that you see a picture of this, our text version of this amplitude. and that's the one. I always think this is a very nice picture and give a nice sort of a, well, to some extent, introduction of this word of the M2 okay? Yeah, let me go back. All right, so this is basically a linear algebra part. So now I will give you sort of another way of defining this using the generators of the totally non-negative or totally positive of the monoid. That's my second part. I want to define the totally non-negative part. And what I actually want to also define the totally non-negative of the flag variety. Okay, and so let's fix some setting to start with. I want to fix a space group over R. Or minimal Casimudi group. The maximal Casimudi group is a little bit more complicated. So the whole setting only works for minimal. Okay, and we fix the pinning. And I want torus, and positive Borel, negative Borel. I want xi and yi for the SO2. And I is the connection of simple root. And example case, you can always keep in mind, is SO2. Well, sort of, sorry, GON case. Okay, so basically, T is diagonal matrices. And the Borel just upper triangular and the lower triangular matrices. Upper triangular and lower triangular. Okay, and basically x1 of A, that's the SO2 here. I basically want this to be 1A1, everything to be 1, and 0 everywhere else. And Y1, I'm assuming my I is just indexed by 1 to n minus 1. 1, everything else, 0. Okay, and AR. Okay, all right, so with here ready, I can define what's the R plus point of the U plus. I will define this to be the monoid. Again, recall I allow multiplication, but there's no inverse. Is the monoid in the R point generated by all the xi. I want A to be R positive, but I want to include identity. I want to add a 0, I in I. So you can notice here, I'm sort of writing this in a very strange way. I'm writing R positive union with 0, and the notion of this will be clear later. Okay, since here R actually have a 0, that's kind of a special case for semifield. So before going to the next part, I mean, you can imagine I may have the upper triangular part. I should have also lower triangular part, the counterpart of this as U minus. And before doing that, I want to actually sort of show you some interesting computation, which is actually very crucial for the generalization here. So just by direct computation using 3x3 matrices, we can see that we have x1a, x2b, x1a. This is going to be x2 bc over a plus c, x1 a plus c, x2 a plus b, a plus c as the example. I'm assuming everything I'm in the GON case. Okay, so you can just do this in the 3x3 example, 3x3 matrices using the example above. So the key thing I want to emphasize is here you can see this expression only have multiplication and division and addition. There's no subtraction. That's really the key thing I want to emphasize. No subtraction. Okay, people call this subtraction free. Okay, as I mentioned, I only have upper triangular part. There should be counterpart to the lower triangular. Let me just complete my definition. This is the monoid inside the group generated by yi of a. Again, I want a to be positive or 0. And I is a simple root. And the torus part, the positive, just the positive one. Monoid generated by alpha check of a, alpha check is the co-root, a is positive. Okay, I am not allowed to have 0 here. And then the totally non-negative part of G, let's see, Tnn, is basically the product of everything. Or you can think of this as the monoid generated by all the 3 components above. And it's not a trivial thing. We actually have some kind of a triangular decomposition, which is basically what I'm writing here. Okay, so now if I taking G to be G of N, I basically give you 2 definitions. Well, I basically give you 2 things in one notation. The better to be the same, otherwise it's going to be some confusing. And yeah, they are the same. I think that's the theorem by Whitney in 1952. I actually don't know this precisely. I think that was mentioned in one of the survey paper by Lucid. So I actually couldn't find this result here. Okay, the 2 definitions of totally non-negative matrices in GLN of R agree. So in other words, if you want to consider the first definition I give you using the minor to be positive or minor to be non-negative, you can actually write down the generator of the monoid. That's basically just by those xi, yi, and the alpha check. Of course, I have some restriction on the entries I'm taking. Okay, and let me take a short pause. Any questions so far? All right, let's move on. So basically now I give you the definition of totally non-negative part of the group. And there is also a definition of totally positive. I'm not really giving you here. And so now the next one, as I promised, I want to give you what's totally non-negative of the flag right here. Okay, and so, I'm sorry. Okay, so we consider first the flag variety, and I'm only interested in the R point. And the definition, the totally non-negative, I will define the totally non-negative to be U minus, I have this, the lower triangular part, if you think of the GON case, of the totally positive or totally non-negative part of the group. I want to this acting on my choosing pinning, B plus, and then I'm choosing the closure. And I want to think of this as closure inside my flag variety. I want to remark here, I'm only taking closure in the Hausdorff topology. Okay, and before giving you example, I want to give you some kind of a, yeah, I think this is one of the most crucial results starting everything. That's a 1994 paper I mentioned. Well, that's the sort of thing I mentioned in the abstract. Static 4. And how to understanding this totally non-negative or totally, yeah, this is good. This is all right. This is totally non-negative flat variety or flat manifold, let's say. Okay. And so one of the fundamental results in Lustig's paper on total positivity here is relating this with the canonical basis. So I'm going to write a statement. I want to mention here Lustig's results there only works for finite types. And if we consider the embedding of the flat variety to the projective space, and this one, this is the projective space of L lambda, everything is over R. I'm using this notation. I want to think of this projective space R point because later I'm going to change everything to be semi-field. So now I'm just temporarily using this notation with upper lambda here. And my lambda is regular. Okay, and then the space we define here is the same as when you do the embedding, and then you can consider the coordinates with respect to canonical basis. All the coordinates are non-negative. Let me write down my notation and then I will explain. Okay. So the interesting part is here. This is, well, I said this in words. I want to consider all the lines such that if I'm considering their expansion in terms of canonical basis, CB of lambda here, I just mean the canonical basis on L lambda. And I want to consider all the lines, all the coefficient here to be positive or 0. Okay, again, same thing here. Basically, whenever I write greater than or equal to 0, I want to think of this as a positive and a 0, since 0 is something a little bit special. Okay, and of course here, since I'm in the projective space, basically plus and minus the same. I'm just saying that there is a representative, everything is positive.
Do you assume simple laced or something?
Pardon? Yes, simple laced. Yes, exactly. Simple laced. Yes. For non-simple laced case, you need to do the folding. Thank you. Yeah. For non-simple laced case, the approach is obtained by folding. Yes. Thank you. I should say basically, I think I'm secretly assuming everything I'm doing here is actually simple laced. Yeah. Appreciate. And I want to say one sentence about the proof that appear later. But before everything going to abstract, I want to give example. Since the whole thing is, well, I showed you one good picture about the amplihedron. I want to show some other nice picture before I say the one sentence about the proof. So basically in the SO2 case, and this flat variety here is just a circle. Suppose I'm choosing here to be my 1, 0. Here to be my orientation. No, I want the other one. This to be 1, 0. Okay, and anything here, I'm thinking as coordinates, projective coordinates, 1a, and here I'm to be 1, negative a, and suppose a to be positive. Or let me still write it this way. Okay, and then with this writing, I'm writing all the coordinates out. It's pretty straightforward. I want the right-hand side to be the totally non-negative part, since that's all the coordinate to be non-negative. You can see you have a negative a here. Okay, so yeah, let me squeeze it here. So then the R point, this is just the right-hand side. Okay, and also there is a SO3 example, and I'm not going to draw the picture. I will just show you the picture in Connie Rich's paper. That's the picture, the totally non-negative of, let me zoom out, let me zoom in. Okay, this is the picture. You'll see this is actually a sphere. And this is not just sphere. We have some funny marks here. I'll explain those. This will actually also come up. All right. And that's the picture. But basically, for many things, I'm saying that this, if you keep this P1 picture in mind, I think, yeah, that's sufficient for many sort of idea, I think. So now I want to say one line of the proof, which is relevant for later. Basically, I won't have the formula here. So let me write this as, right, I need to match with my notes. Yeah. Proof of the theorem. I'm gonna have a quotation, and basically this is very simplified. I just want you to see the flavor, and also one of the equation will come up later. And basically, I want to explain why this totally non-negative part defined using the closure is actually lies in the right-hand side. Or in other words, sorry. Yeah. Okay. Let me zoom out. Yeah. So basically, now here we have this to be isomorphic to the intersection, and basically identify this with the image here. So I'm sort of want to convince you why the image lies in this. I'm calling this totally non-negative part of the projective space. Why all the coordinates are positive, and that's exactly because action on the canonical basis is positive. Okay. So recall this really we have the embedding here. And I'm adding yi, that's 1, we map to the line. E lambda, this is the highest weight. So if you write out this action, this will just be CB act on the canonical basis. And the coefficient is always positive. And this is usually what I mean, positivity of canonical basis. What I really mean is the action, and you don't have to restrict yourself to the highest weight. You can generalize this to anything. And so one remark I want to make is, and here, if you want to do the detailed computation, this CB, or if you sort of changing this to the algebra and using this as exponential, this is not just a positive. You can actually write out what this look like. This is actually integer coefficient with n tracing A. Okay, positive integer coefficients, right? I want a natural number coefficient with n tracing A. Okay, and yeah, that's basically my one-line proof for this direction. Very sketchy one. The only thing is I want to have this formula coming out, and you see the action will give you something with positive integer as coefficient and polynomial with n tracing A. Okay, any question so far? So this is basically one flavor of the definition over the semifield positive real number, even though I still haven't give you the definition semifield. You can imagine a little bit, but basically R plus is a typical example. So one of the property like this is something we want to keep. I will also want to, next, I want to explain another property, which is crucial to the structure here. And that's basically relevant to the picture in the continuations paper. Okay, so basically this is not just some topological space, it's actually a CW complex. It's actually a regular CW complex. I want to explain the CW complex structure. That's basically the next part. That's my third part. Yeah. Sorry, that's my third part. Cellular decomposition of the totally non-negative part. And this decomposition was conjectured just in Lucy's paper in 94. And this was proved by Connie Risch in 97. Okay, let me explain this, and I will also refer back to Connie Risch's paper. You'll see sort of picture-wise what it corresponds to. And so I want to start with two elements in the while group. This is one group. Okay, and we define. I want to have a stratification. Define BVW, and I want this to be B minus the opposite supercell intersecting with B plus W, B plus, and I'm intersecting everything with the totally non-negative part. And this is non-empty, only one. V is less than equal to W. And as non-trivial without, this is actually homomorphic to R positive of length of W minus length of V. So topologically, it's trivial. And we have just basically follow from the decomposition of the flag variety. We have the totally non-negative is a disjoint union of BVW of R plus. Okay, and now getting back to the picture in continuation, you can see here this line. You can imagine that's pretty much just the BVW. I'm choosing S2 to S2 S1, and the difference is 1. So here it's one-dimensional. I'm not including the endpoint. The endpoint here should be S2 to S2. That's 0-dimensional. Okay, and also there's a big triangle. Let's call it triangle here, and just from S2 to S1, S2 S1. Okay, and you can also see the open sphere here is basically from identity to S1, S2, S1. Okay, and it's non-trivial without, everything is topological trivial, and it's even non-trivial, it's even more non-trivial. This is a regular state W complex. This is a theorem by Galashin, Karp, and Lamb. This is only from 2 years ago, not last year anymore, 2 years ago. The totally non-negative is a regular stable complex. Regular stable complex. Homomorphic to a closed ball. Okay, the regularity really is the hardest part. To prove it is stable complex is not very hard. Basically, you want to use certain trick about I think to prove it's stable complex, there are certain trick in I think in continuation, Lauren Williams' paper, in some other places. Generally, there are certain positivity regarding the canonical basis. You can typically prove this is the CW complex. The regularity is really very hard without here. Okay, so you don't have any strange CW complex coming up. Okay, so that's basically the decomposition. But however, I really don't want to think of this in the so geometric way, since later when I sort of changing this R plus to be something else, I don't really have this nice geometric picture. So I want to have another way to have this decomposition. So I'm going to give you a concrete version of this, a concrete parametrization of each of those strata here. Okay, so next I want to give you an explicit parametrization of, well, this is just the positive ratios of variety. And I only want to explain this by example, since at the end there's some kind of a combinatorics algorithm comes in here. I think example is clear enough. And this is by Risch and Marsh in 2004. Okay, I'm gonna do this case in S3 case. I want to choose my W to be S1, S2, S1. But for this, in order to be work, I want to give you a concrete parameter. So in other words, let me explain what I want to try to do. I want to give you a concrete isomorphism. Why this is isomorphic to the R positive to the power of the length, a difference of the length. So I want to give you a concrete parametrization from positive R to the space here. So to do this, I want to actually not just fix the W, I want to fix the reduced expression. Actually matters a little bit here. Let me have underline. So for another reduced expression, I'm writing W prime even though it's the same element. but I want to emphasize I'm having a different reduced expression here. Okay, and I'm choosing V to be S1. This is less than or equal to W, whatever version you choose. And I want to think of this as a sub-expression of W. I want to think of this as a rightmost sub-expression. So I think of this as 1 times S1. I don't want to pick S1 times 1 times 1. And for the second one, there's no flexibility. This is a positive sub-expression in a more technical way of V in W, or more technically, it's W underline. Okay, or underline prime, not underline prime. Yeah, let me ignore here. Okay, and then once we have this parameterization, then we can define for each parameterization, for each expression here, we can define a concrete map. We can define GV or W. And since this positive expression is unique, I want to choose this to be rightmost. So, well, I don't think it's that obvious, but you can just convince yourself the rightmost one, since I'm sort of pushing everything to the right, it's a unique one. So in writing this notation here, I don't need to specify the expression for V, only for W. I want to define this to be Y1 of A, Y2 of B, S1 dot. This is the left while group element. I'll give you a concrete version in a minute. I want AB only to be positive or 0. Only positive, sorry. I don't want 0. I want this act on B plus. And this is something, actually, this is non-trivial claim. This is a part of this non-trivial thing. This is a part of theory in the Marsh this Rich and Marsh paper. This is actually precisely the positive ratios are right here. Okay, you can see this is actually going to be R squared. Oh, sorry. Okay, this is actually just going to be R times R. And this here, I want to have a very important remark. S1 dot, this left, somehow I want to sort of matching everything with positive. I want to choose x1 negative 1, y1 1, x1 negative 1. In terms of matrices, it's just 0 negative 1 0 1. Okay, and as a non-trivial statement here is if we choose different expression, of course, at the early definition on the right hand side, I'm not referring anything to the reduced expression. So as non-trivial statement or as expectation, everything should be independent of the reduced expression. But that's actually a non-trivial statement. Y2A, S1 dot, Y2 of B, AB, positive, and this is the same. Okay, this is just a concrete parameterization, how concretely we're writing things out. And this depends on a fixed reduced expression of W. And so now I've been keeping emphasizing everything should be positive. I want a positive expression. I want a positive real number. Everything is like totally positive or totally non-negative. And now, unfortunately, you can see here we have -1. Just to make it clear, recall -1 is not positive. And this is actually one of the things causing huge issue for later construction. We have to replace this by something else. Okay, let me take a short pause. Any questions so far? I'm gonna move on to give you definition semifield. And basically, I want to repeat most of the thing and then define everything over arbitrary semifield instead of over positive real number. Okay, let me continue then. So now I'm going to give you formally the definition of semifields and with examples. So basically, this is an example of semifields. And typically, it's just a K. We have two operations, addition and multiplication. I want this to be a monoid. Sorry, let me have a circle. I want this multiplication to be a group. So inside positive real number, basically, the addition, just a normal addition, multiplication, just multiplication. We can always take an inverse on multiplication if we have positive real number, but we cannot do the inverse on the monoid since the inverse is going to be negative real number, which I don't take here. So it's only monoid here. And a very important non-trivial example is really the tropical integer. Okay, the addition I'm taking is taking the minimum of two integers, and the multiplication I'm taking is taking the normal addition here. And so, well, it's very easy to convince yourself. Taking minimum of two elements, there's no way to do inverse here. And taking addition inside integer is actually invertible. We have negative integer here. And another important example in this case is a single point. This is the semifield of one element. Okay, and the operation is pretty obvious. There's nothing else we can do. Okay, so now the question or the punchline: how to define the flag variety with a point in the semifield? Okay, and basically you've seen one example, we can define this over positive real number. But one of the very important thing is we actually have a field containing positive real number, which is just the odd real number. But in this case, you can easily see since if addition has no cancellation, there's no way this can be contained in the field. So the normal approach would not work. We have to try something different. Okay, but however, at the end, there's still various property we want to keep. We want a certain compatibility with the canonical basis, or in other words, with the projected space. We also want to have there's a cellular decomposition, and more importantly, we also want the group action, or more precisely, the monoid action. So next, we define BK. Okay, so basically now I'm going to repeating a few things. We still fix the G with pinning. Yeah, as Lucy commented earlier, I should assume everything to be simply laced. If it's not simply laced, everything should be folding. And again, you can assume this is just in the GON case, even though this could be minimal cascoding. And the definition of this monoid is due to Lustig. And you can see we basically can copy over everything we did earlier. But now, since I don't really have a group to start with, I have to start with a free monoid generating just by its element. And my semifield generally does not contain element 0, but I somehow want to artificially adding element 0 here. You can think of this, if we plug in 0, this somehow become identity. Okay, you can imagine sort of how to do the operation if I artificially adding a 0 element. So it's sort of absorbing everything. And then since I'm starting with a free monoid, I need to specify what relation I have. That's also this is sort of the reason I give you the computation earlier over the GO3. And if you recall, in GO3, we have x1a, x2b, x1c. The commutative relation is basically b times c over a plus c. But now I don't want to do multiplication. I don't want to do addition. I just want to change everything to the operation in the semifield. And then just mod it out. I give you only one relation. You can write out the other things. And we're sort of following this up. We define this for U minus part, define this for torus part. And then basically we want to consider the monoid generated by all those together. Okay. And it's actually already immediately not obvious once you define everything. The size is actually as expected. And I didn't really emphasize this, mainly for time reason. And the size of this U plus, there is actually an estimated size what this look like is the disjoint union of K to the length of W. And over R plus, This is actually very easy to prove because we know secretly we have a field of real number, and you can do multiplication by xi inverse, sort of you can moving things back and forth. And over arbitrary semifield, this is actually really non-trivial, and this is the consequence of some theory I'm going to give you later. The size is actually correct.
Excuse me, if A and C are 0, it doesn't make sense, this relation, no?
Pardon?
If A and C are both 0, then it doesn't make sense.
Oh, no, I don't want, if A and C are 0, this relation doesn't make any sense. If it's 0, this doesn't make any sense. But if I'm taking this to be, yes, I want 0 to be identity. Yes, thank you. Yeah, and yeah, x0 to be identity. Yeah, thank you.
No, but the relation doesn't make sense even now.
I think you just don't do the relation, right? I think I copied. Yes, I see your point. I see your point. I'm trying to figure out where I had a mistake here. I don't want this to be 0 exactly. So I think this relation above is only for ABC does not be 0. Yeah, this relation should be only for this not to be 0. And if plug in 0, yes, as I commented earlier, I want this to be, yeah, exactly. But the point is, I still want to keep the identity element inside my U plus of K. That's the point. I want to have a 0 here. But yes, the relation, I don't really need to consider this to be 0, since that's just identity element. Yeah, I think I'm good now. Yeah, appreciate it. Any other question or comments? Okay, let's continue. And yeah, okay, that's here. So now the definition, we don't really have a flag right here. We cannot do the quotient. It's not a group. The quotient doesn't make any sense here. So what we can do is really following the theory I gave you earlier on Lustig. We try to define this. We want to define the projective space first, because this one for any dominant regular regular dominant lambda, we want to define the projective space or the projective space over the semifield. Basically, formally, just consider formally elements as spanned by the canonical basis element with entries in K. And again, I'm sort of adding a 0 here. If it's 0, it just means this coordinate does not exist. And then sort of I want to mod out the K star action. And recall, this is actually a multiplicative group. So this is actually fine. So you can think of this as formally still as a line here. Even though technically this is just a K to the dimension of L lambda. But the reason I want to have this writing in this expression here is because then I can use this expression to define the action of the monoid GK. This is basically copying over the one sentence proof I have earlier. If you recall, I have a GR acting on this. This YIA acting on, I'm giving you an example case only in highest weight. All the entry is a positive integer polynomial with entries in A, like here. So then we just copy over this, define this over semifield just by changing all the operation to the semifield operation. Because here you can see I only have multiplication and addition, nothing else. There's no subtraction. So I can just copy everything over to the right-hand side and define action. Okay, yeah, I think this is already defined in Lustig's, one of the Lustig's paper. I think there was a sequel paper on this subject. And so then with this definition here, I can define the cellular decomposition of the flag variety, or more precisely, we can define the cellular decomposition sort of on the projective space here. And then expect we have the flag variety out of this somewhere. So then this is really the Marsh ratio parametrization or ratio Marsh parametrization I commented earlier. And just to copy over the same example, I'm having W to be S1, S2, S1. Again, if you recall, I want to fix reduced expression. I want to have V to be S1, this to be rightmost reduced expression, S1 and S1 here, same as before. So now I can define the action on the projective space of the monoid. I can define Y1 of A, Y2 of B, and everything. But if you recall earlier, we do need to have the left of Y group, which requires X1 of -1. And this is not positive. So instead, the way we bypass this is we consider the Cauchy operator on the canonical basis. This is really operator on the set. We just expanded this k linearly, and then this is the well-defined action. We can have this acting on the projective space or just act on the highest weight vector. And then this naturally will define as a subset here. And for different reduced expression, I can copy this over, define another expression. But now you can see that earlier this non-trivial theorem, it's the same thing. But now it's totally unclear why in this definition they actually should coincide, because earlier we have all the other two available, but now it's just just definition here so far. Okay. But now if you recall earlier, we have this flag variety or the totally positive, totally non-negative part as a union of each of the positive Richardson. We can sort of taking each one of those as the BVW and union them together. But this depends on reduced expression. So what we take is for any wild group element, we fix reduced expression. And so that's my notation W here. And then for that, for each V less than that, since it's a positive sub expression or the rightmost, there's no sort of a choice on V anymore. I'm taking the union of this on the right-hand side. The whole thing should be lies inside the P lambda. And first is the Horval notation. This is upper lambda, this is upper W. So the theorem we have, as I mentioned, basically the whole talk is justified, definition is correct. And the subset inside the projective space here is independent of the choice of reduced expression of W. So in other words, those two sets actually coincide inside here. So, and also this is a disjoint union. And even from this definition, it's unclear. Even from this definition, it's unclear if I choose different V, different VW, they actually disjoint. So this is actually disjoint union. And also secretly, there should be a dependence on lambda. This is actually also independent of lambda because once everything is over semifield, this actual projection map from lambda plus lambda prime to lambda. Okay, in general, if this is over field, this is only a rational map. But in over semifield, you can actually define this. Okay, for time reason, let me not comment on that. And then another non-trivial thing is, if you recall, we actually define a GK action on the projective space here. This subset we define is actually stable. This corresponds to the fact that the totally non-negative part over the case over positive real number is invariant under the totally non-negative monoid of the group. This is the counterpart for R. And a third, everything is actually functorial. And we don't have to plug in this. You can sort of consider this for K, and you can change everything simultaneously for some other thing. And it's a functorial relation here. And the most interesting, of course, is this from the polynomial R to the tropical Z. Okay, and at the end, to justify everything is correct, if I'm taking K to be positive real number, we recover everything. Of course, I'm sort of cheating a little bit, since in this setting, you don't any say topological structure here. Okay, we sort of know there is a sort of a topology on R. Okay, but let me mention the key thing is really sort of the three items in the theorem, and the last four is just sort of justify everything works. And at the end, some final remarks. The tropical Grassmannian case is actually defined earlier by the Speyer and Williams already, and their approach is actually quite different. I think the result is actually also slightly different than ours. And overall, as I mentioned, this whole thing is sort of initiated by a sequel paper by Lustig. I think his motivation is trying to, correct me if I'm wrong, try to establish a property on 1 and 2 and also on 3, and sort of have the action of the monoid and also have the cellular decomposition. I think Lustig managed to do this for the 3 cases. And of course, this is the original case. And his approach using the topology of R, basically using topology of R, you can give a topology on the function here, and also doing the base change or sort of doing the functorial statement, you can also obtain on tropical Z. Okay, but our method can deal with arbitrary semifield. And I'm not giving you anything about the proof, so I just want to mention, even though I just want to mention nothing, this is not really a trivial statement. The case of partial flag, we really don't know how to do this. Okay, everything above is really only for full flag variety. Okay, and thank you. That's end my talk.
Are there any questions? Okay. I had a question. Is it still true this this dimension formula with the difference of the lengths for a general semifield?
Dimension formula.
Or you know, each of these.
You mean this one?
Right, correct.
Yes, it's also correct. Just from this expression here, you only have two dimension. Exactly. Yeah, that's a good question. Thank you. Yes. Yeah. Okay. There's a question on the chat.
No, it's just
oh, okay. Never mind. Yeah. Okay. Yeah.
Any other questions? If there's no other questions, let's thank Huanchen again.
Okay, thank you very much.